Welcome back to CAP 6640. Today we will begin with a light introductory overview of natural language processing. We will start by providing some historical background, then move on to discussing the core NLP tasks and the categories they belong to. From there, this lecture will serve as a bridge toward what we will cover in the next lecture, where we focus on usable meanings and language representations. Here are the objectives of this lecture. We will begin by tracing the historical evolution of natural language processing, with particular attention to the major paradigm shifts the field has undergone from symbolic and statistical analysis to modern deep learning-based approaches. Next, we will examine why understanding natural language is inherently difficult. We will then distinguish between syntactic, semantic, and pragmatic NLP tasks, discuss the types of problems associated with each category, and finally identify core NLP tasks along with their real-world applications. Before we get started, let me briefly cover a few logistics items. Module 0 and Module 1 have been released. The lecture recordings will be made available shortly after each lecture for those who wish to use them. Several of you asked about a recommended textbook. That information has also been posted. The recommended book is an open source text. While it does not cover every topic we will discuss in this course, it provides a solid foundation for many of the core concepts. The academic activity has already been posted and is due on January 23rd. This activity is worth 13 raw points, which corresponds to approximately 1.3% of the overall course grade, and it counts as a bonus. I strongly encourage everyone to complete it, even if you do not need it for financial aid purposes. Assignment 1 has also been released and is due on January 26th. Finally, the project proposal was originally scheduled to be due on January 19th. However, since January 19th is a national holiday and university policy does not allow assignments to be due on holiday, the new due date will be January 20th. Before we get started, are there any questions or comments? Here's a question about the academic activity. Let me briefly clarify one point regarding the academic activity. This assignment is a bonus assignment. When I say bonus, I mean that if you complete it, the points are added on top of your grade. If you choose not to complete it, there is no penalty. You can think of it as an extra credit type assignment. This point is very important, so please pay close attention. Please use email for all course communication. You can reach me at Mohaisen@ucf.edu or David Mohaisen@ucf.edu. Any university-associated email address you find for me will reach the same inbox, so feel free to use whichever one is convenient. The reason for this is simple. While I understand the appeal of using web courses for communication, it is not the most effective or intuitive tool for me to track conversations. If you use email, you will receive a response much more quickly. If you use other platforms, I will likely still respond, but it may take longer. With that, let's get started. We will begin with the historical background of natural language processing. For those of you who have been closely following recent advances in AI, particularly in natural language processing and large language models, it may seem as though NLP is largely a product of the last 5 years. In reality, that is not the case. Natural language processing as an idea dates back to the 1950s. At that time, NLP and computational linguistics more broadly began to emerge as formal disciplines. Early on, language understanding was believed to be a relatively simple computational problem. The prevailing assumption was that language could be captured using a small number of handcrafted rules supported by basic statistics, and that these rules would be sufficient to build effective systems. This assumption turned out to be far from the truth. After the initial enthusiasm, it became clear that natural language understanding is an extremely difficult problem. Machine translation, for example, which involves mapping a sequence in one language to a corresponding sequence in another language, was widely considered infeasible. Researchers struggled to find reliable mappings or bridges between languages. As a result, many researchers working in this area during the 1960s and 1970s abandoned the broader goal of language understanding and instead focused on narrow language-specific problems, such as grammar modeling. This period is commonly referred to as the dark age of natural language processing, spanning much of the 1960s and 1970s. Moving into the 1980s, we begin to see a slow revival in the field. Much of the work during this period focused on the science of language itself, namely linguistics, with an emphasis on studying language structure, grammars, and formal characterizations. The late 1980s and early 1990s marked a major turning point and the real boom of computational natural language processing. This period saw a revolution in statistical modeling of language. These advances were closely tied to the rapid increase in computational computational power, particularly with the widespread adoption of personal computers. Throughout the 1990s, continued improvements in both personal computing and back-end supercomputers enabled data-driven approaches to flourish. Researchers began ingesting large amounts of text from the same language, organized into corpora, and using them to build statistical models. These approaches moved the field away from the purely handcrafted rule-based systems of the 1950s toward learned representation. From there, progress continued steadily. With the advent of the internet and the accumulation of massive multilingual datasets, language models increasingly relied on real-world data augmented by linguistic insights. This led to improved performance and more sophisticated statistical techniques for characterizing language. Except by the 2010s, representation learning became a central driver of progress. Learning techniques began to automatically combine statistical patterns, linguistic structure, and contextual information, particularly with the rise of deep learning-based approaches. Before moving on, let me address a question about what we mean by linguistics. Linguistics is the scientific study of language. It focuses on understanding and characterizing languages and is traditionally considered part of the humanities rather than computer science or computation. For example, linguistics examines how languages are grouped into families, how their structures are organized, and how syntax and grammar operate. It studies the rules that govern language, whether those rules are universal or language-specific, and how different languages relate to one another based on these rules. We will touch on some of these aspects again when we discuss NLP task categories shortly. The key distinction we are making here is between linguistics and computational or statistical approaches to language. Linguistics studies language as a scientific object in its own right, while computational approaches aim to characterize language behavior using statistical, algorithmic, and computational methods. That said, these two perspectives are not disconnected. In fact, one of the most influential figures bridging linguistics and computer science is Noam Chomsky, who made foundational contributions to both fields. For example, he introduced context-free grammars, or CFGs, which remain central to both linguistic theory and computational language processing. Another question is whether the recent rise of large language models represents a kind of renaissance for natural language processing. In many ways, the answer is yes. We are currently witnessing a period of remarkable progress. Even if development were to slow down from here, the capabilities of modern large language models already enable a wide range of tasks to be performed extremely well. Importantly, these advances did not emerge overnight. They are the result of cumulative progress over decades, building on ideas from the statistical and computational work of the 1970s and 1980s through the data-driven approaches of the 1990s and 2000s and into today's large-scale language model. What we see now is the outcome of this long accumulation of knowledge and methodology, culminating in the language models we use today. From a computer science perspective, we are not here for a detailed history lesson. However, in computational terms, the early foundations of the field trace back to the 1950s. For computer scientists, this period begins with Alan Turing, who proposed the concept of machine intelligence in his seminal work, Computing Machinery and Intelligence. In that work, he introduced what we now call the Turing test as a way to evaluate a machine's ability to exhibit intelligent behavior. Following that, in 1954, the Georgetown IBM experiment demonstrated the first machine translation system, successfully translating 60 Russian sentences into English. By today's standards, this may seem like a very limited task, but at the time, it represented an important milestone. It highlighted one of the earliest advances in machine learning, particularly in the context of natural language processing. So, for us as computer scientists, this places the initial foundations in the 1950s. Moving into the 1960s through the early 1980s, natural language processing was largely dominated by relatively simplistic systems based on handcrafted rules. These are what we commonly refer to as symbolic systems. In such systems, language processing is driven by explicit rules. For example, if a particular pattern appears in the input, then a predefined action is triggered. These symbolic approaches relied heavily on grammar-driven rules. For instance, if a word appears at the beginning of a sentence, the system might apply a specific grammatical expectation or constraint based on that position. A major influence during this period was the work of Noam Chomsky, whose grammatical theories shaped both linguistic modeling and early rule-based approaches to language analysis. One particularly important contribution is the notion of context-free grammars, or CFGs, which we will cover in a dedicated part of this course. Another notable milestone from this era is the work of Joseph Weizenbaum, who created ELIZA in 1966. ELIZA was one of the earliest chatbot programs and simulated aspects of a psychotherapist through pattern matching and scripted instant responses. This period, spanning roughly the 1960s through the early 1980s, reflects the dominance of symbolic rule-based thinking, while the foundational ideas emerged in the 1950s. Much of the early practical work during this time focused on these handcrafted, grammar-driven approaches. For a long period of time, spanning roughly the 1960s through the 1980s, progress in the field was relatively limited. There were a few notable highlights, but overall activity and impact remained modest. This began to change in the late 1980s and into the 1990s, when statistical methods started to replace purely rule-based systems. Around this time, techniques such as principal component analysis, or PCA, began finding applications in natural language processing and machine learning more broadly. While PCA itself is an older tool, its practical use in NLP emerged in the late 1980s and gained traction through the 1990s. As researchers gained access to larger data sets and increased computational power, they were motivated to explore new tools that could model and characterize language more effectively across a range of applications. Another major development during this period was the introduction of hidden Markov models, or HAMs. These became an important statistical framework, particularly for speech and text processing, and saw widespread adoption beginning in the late 1980s. At the same time, the creation of large, structured datasets played a critical role. One notable example is the Penn Tree Bank, developed by Mitchell Marcus and collaborators. This resource provided carefully annotated corpora for training and evaluating models, and marked a serious turning point toward the data-driven approaches that underpin much of modern NLP today. Then, moving into the 1990s and the early 2000s, large-scale NLP really began to flourish. During this period, algorithms such as n-grams and log-linear models became widely used, leading to significant improvements in tasks like machine translation and speech recognition. We will spend a fair amount of time in this course discussing n-gram models in detail. One important clarification here is what we mean by statistical NLP, especially in contrast to symbolic NLP. That is symbolic NLP. In statistical NLP, we start with data and compute statistical characteristics over that data. This includes modeling how often characters, words, and sentences appear and co-occur within a corpus. For example, if you take a large text such as a book and build a language model from it, the model would first identify the vocabulary based on word occurrences. It would then estimate how frequently words appear together to form sentences. These frequency-based patterns form the basis of a statistical language model. We will revisit this idea in more depth later. This approach contrasts with other modeling paradigms such as neural network-based models. At a high level, statistical models rely on explicit probability estimates derived from observed data, whereas neural models learn abstract representations that implicitly capture these patterns. A related question often comes up regarding the difference between systems like Google Translate and models such as ChatGPT. Today, there is essentially no fundamental difference in terms of modeling paradigm. Modern Google Translate systems are also based on neural network models. Historically, however, this was not the case. Earlier versions of Google Translate relied heavily on statistical machine translation methods rather than neural networks. ChatGPT, on the other hand, was developed directly using neural network-based approaches. At present, both systems rely on neural models, even though their historical development paths were different. So, to summarize, while there used to be a clear distinction between statistical machine translation systems and neural language models, that distinction has largely disappeared in modern systems. That covers much of the early work in the 2000s. If you recall, Google Translate emerged around 2006. Around that time, the community also began to formalize evaluation criteria for these models, leading to the development of the BLUE score. We will discuss BLUE in more detail later in the semester. It was introduced by Kishore Papineni and colleagues and became the standard evaluation metric for machine translation. While it is not the best metric by today's standard, and we now have better task-specific evaluation methods, it represented an important step forward when it was introduced in 2002. Notable advances during this period also include the early versions of Google Translate in 2006 and 2007, which relied on statistical machine translation methods. Today, Google Translate no longer uses purely statistical approaches. It is based on neural network models and incorporates techniques such as transfer learning and reinforcement learning, which we will discuss later in the course. Many of the advances we see today, including systems like ChatGPT, are largely the result of work that began after 2009 and 2010. There is a clear turning point during this period, driven by breakthroughs in deep learning. One of the most influential milestones was the work that led to AlexNet in 2009 and 2010, developed by Alex Krzyzewski at the University of Toronto under the supervision supervision of Geoffrey Hinton. Hinton is well known for his contributions to neural networks and deep learning. While backpropagation itself is an older idea, his work demonstrated how to use it effectively at scale. This led to a major breakthrough in computer vision, particularly in image classification. AlexNet showed how a convolutional neural network could automatically learn mappings from raw images to object categories using large datasets such as Imagen. This was a significant breakthrough, not because it invented entirely new ideas, but because it refined and combined existing ones in a powerful way. From there, progress accelerated rapidly. We saw advances in representation learning, including early word representations such as WordNet, which we will cover in the next lecture. We also saw the use of large-scale datasets, improvements in deep neural networks, and later models such as BERT. Many of the systems we use today are direct descendants of this wave of innovation that began around 2009 and 2010. Following this, word embeddings became a central concept in NLP. The data declarative WordNet, introduced in 2013, fundamentally changed how semantic relationships between words are modeled. Instead of representing a word simply as a sequence of characters or discrete symbol, words are mapped to vectors in a continuous space that capture rich semantic and syntactic properties. Sequence modeling also became much more effective during this period. While ideas such as recurrent neural network date back to the 1990s, including work from the late 1990s, their practical success in language modeling came later, around 2013 and 2014, with architectures such as LSTMs and GRUS. These models enabled substantial improvements in tasks like language modeling and machine translation. It is worth noting that the invention and credit for LSTMs has been the subject of debate. In particular, Jürgen Schmidhuber has been vocal about attribution, especially in light of major awards such as the Turing Award being associated with this line of work. Despite the debate, there is no question that these contributions have had enormous impact, as reflected in their widespread adoption and very high citation counts. Now, this historical overview is useful, but this course is not really about history. The goal here is to introduce the core tasks that we will study throughout the semester, place them in the right context, and on top of that, explain why these tasks matter and why we study them. At first glance, language may not seem particularly difficult. We all speak at least one language, whether it is English, Arabic, Korean, or others. Because we use language naturally every day, it often feels like its rules are clear, well-defined, and easy to follow. This naturally raises the question, if humans understand language so well, why could we not simply computerize it, especially as early as the 1950s, when computers already existed? The difficulty does not stem from limitations of computers themselves, such as memory or representation. Rather, it lies in the nature of language. Languages are highly contextual. Words on their own do not carry complete meaning. Meaning depends heavily on context, intention, and usage. A single statement can convey different meanings, depending on tone, situation, or background knowledge. Languages are rich, expressive, and inherently ambiguous by design. They allow multiple interpretations and often rely on unstated assumptions. Languages are also diverse. While it might be possible to build a very effective model for one or two languages, there are thousands of languages worldwide, each with its own structure, conventions, and quirks. Some languages are difficult to describe using a clean, closed-form set of rules, and in some cases, they do not conform neatly to fixed grammatical systems. Ambiguity plays a major role as well. A single word can have multiple meanings depending on context. In Arabic, for example, this contextual richness is a defining feature of the language, shared with many other older languages. Meaning often depends not just on surrounding words, but on broader discourse and cultural context. Language understanding also frequently requires reasoning beyond explicitly stated information. It often relies on world knowledge. For instance, the phrase compound interest carries meaning that depends on an understanding of finance, not just the literal words themselves. Importantly, language can be difficult even for humans. In some languages, native speakers themselves struggle with formal usage. For example, in Korea, the lowest average scores in high school exams are often in the Korean language, despite students being native speakers. Similar challenges exist for languages such as Mandarin and Arabic. Even languages perceived as relatively accessible, like English, still contain significant complexity. Writing systems add another layer of difficulty. Some languages historically required thousands of characters, leading to the development of simplified or alternative writing systems. Korean, for example, transitioned from older character-based systems to Hangul, which uses a much smaller and more systematic alphabet. In summary, text can be ambiguous, meanings can be implicit, understanding often requires world knowledge, and language can be challenging even even for native speakers. These characteristics together explain why natural language processing as a computational problem is inherently difficult and why modeling language accurately has remained a long-standing challenge. Let's look at a concrete example. Ambiguity combines to generate a large number of possible interpretations. Or in English, if you say, "I saw the man with the telescope," the sentence already has two possible passes. Did I use the telescope to see the man, or did I see a man who was carrying a telescope? If you extend the sentence slightly and say, "I saw the man on the hill with the telescope," the number of possible passes increases to 5. Adding phrases such as "on the hill" introduces additional attachment possibilities. As the sentence grows longer, the ambiguity increases rapidly. For example, a sentence like "I saw the man on the hill in Texas with a telescope" can have 14 possible passes. If you add even more detail, such as "at noon," the number of possible interpretations can grow to dozens. The key point here is that as the length of a sentence increases, the number of possible passes does not grow linearly. Instead, it grows combinatorially, often in an exponential manner. From a computational perspective, this explosion of possibilities makes language understanding extremely challenging. So if language is this challenging even for humans, it is even more difficult for computers. That said, this course is not focused on repeatedly emphasizing how hard the problem is. We take that as a given. Instead, the goal is to focus on why we are here, to learn about a set of interesting and powerful tasks that computers can perform with language, and to understand how these tasks are approached in practice. These tasks pertain to understanding language. In natural language processing, we typically divide tasks into 3 broad categories: syntactic tasks, semantic tasks, and pragmatic tasks. Syntactic tasks come from the notion of syntax, which refers to structure. These tasks focus on the structure and grammar of language. For example, dividing a sentence into parts of speech is a syntactic task. Analyzing dependencies, such as determining which words depend on or modify other words in a sentence, is also a syntactic task. Tokenization, which involves breaking a long sequence of text into smaller units, is another syntactic operation. Tokenization does not have to operate only at the word level. While words are structural units, tokenization can also be performed at higher levels of linguistic structure, such as noun phrases or verb phrases. You can think of words as units of language, phrases as units of sentences, sentences as units of paragraphs, and paragraphs as larger units of discourse. From this perspective, tokenization can occur at multiple structural levels. Overall, syntax is concerned with structure and grammar. The second category is semantic tasks. Semantics refers to meaning. These tasks focus on interpreting the meaning of a given utterance. An utterance is simply a sequence of words, and the goal is to determine what those words mean collectively. Semantic tasks often involve identifying the role that parts of an utterance play. For example, an utterance may mention an entity. An entity is a real-world object, such as a person, a place, or an organization. In many cases, we need to identify and classify entities in text. For instance, if a sentence refers to Central Florida, it could mean the University of Central Florida, the geographic region, or some other entity entirely. Identifying and categorizing such references is known as named entity recognition. Semantic tasks also include entity disambiguation, where the goal is to determine what a specific entity refers to in context. Sentiment analysis is another semantic task. Given a piece of text, the goal is to determine whether it expresses positive or negative sentiment or emotion such as anger, care, or hostility. Summarization is also a semantic task, where the objective is to condense a paragraph or document while preserving its core meaning. Applications of semantic tasks include search engines, chatbots, and recommendation systems. In contrast, syntactic tasks often support applications such as grammar checkers and pre-processing pipelines. The third category is pragmatic tasks. Pragmatics combines syntax and semantics but goes beyond them by incorporating context, intent, and implied meaning. Pragmatic tasks focus not just on what is explicitly said, but on what is intended. A key example is coreference resolution. Here, the goal is to determine when different expressions refer to the same entity. For instance, deciding whether a pronoun such as he refers to a specific person mentioned earlier in the text requires understanding context and intent. Similarly, resolving whether the word bank refers to a financial institution or the side of a river depends on pragmatic context. While semantic tasks focus on extracting meaning in a general sense, pragmatic tasks aim to infer intent and context-dependent meaning. Dialogue management is another example, where the system must track context across turns in a conversation to maintain coherence. Discourse analysis analysis similarly focuses on understanding how meaning evolves across sentences and larger text spans. In summary, syntactic tasks focus on structure, semantic tasks focus on meaning, and pragmatic tasks focus on intent and context. Throughout this course, we will study these categories in detail and examine how different NLP systems address each type of task. We will go into more detail, but syntactic tasks are fundamentally about structure. One common example is part of speech tagging, where we identify the grammatical category of each word, such as whether it is a noun, a verb, or an adjective. This directly captures the structural properties of language. Another example is dependency parsing, which maps syntactic structure by identifying relationships between words, such as subject, verb, and verb-object relationship within a sentence. We also consider sentence splitting and tokenization, sometimes referred to more broadly as segmentation. This involves breaking text into sentences and words, or even larger structural units to prepare it for further analysis. Typical applications of syntactic processing include grammar checkers, such as Grammarly, as well as sentence restructuring and pre-processing stages that support downstream language modeling and other NLP tasks. Let's go over a few tasks in more details. One important example is word segmentation. This involves breaking a sequence of characters into meaningful words. In English, this is often straightforward because words are typically separated by spaces. However, in many other languages, such as Chinese, Arabic, and even Korean, word boundaries are not always explicitly marked, and segmentation becomes a non-trivial problem. In some written languages, such as Chinese, words are not separated by spaces at all. In Arabic, words can be concatenated with prefixes and suffixes, making segmentation challenging. Even in English, separators are not limited to whitespace. Characters such as commas, semicolons, or other symbols can play a role in delimiting words and phrases. A practical example of this comes from domain names. Consider a domain like jumptheshark.com. Domain names do not allow spaces, yet they often encode meaningful phrases. To understand the meaning of such a domain name, a system must be able to segment it correctly into its constituent words, in this case, jump, they, and shark. Similarly, parsing strings such as myspace.com, pluckers wingbar, or longer concatenations requires accurate segmentation to infer the intended meaning. Depending on how the string is segmented, different interpretations may emerge. This highlights how syntactic segmentation plays a crucial role in enabling higher-level language understanding. Another important example is morphological analysis. Morphology is the branch of linguistics that studies the internal structure of words. It focuses on how words are formed and how their components contribute to meaning. A morpheme is the smallest linguistic unit that carries semantic meaning. For example, words can be decomposed into prefixes, roots, and suffixes. A prefix such as pre indicates before. A suffix like ed often marks past tense, while s may indicate plurality. Similarly, like can transform an adjective into an adverb, and can indicate comparison or agency. Morphological analysis as a syntactic task involves segmenting words into their constituent morphemes. By doing so, we can better understand both the structure and meaning of words. For instance, the word carried can be analyzed as carry plus, ed indicating past tense. The word independently can be decomposed into in for negation, depend as the root, and lie indicating an adverbial form. Even coined or modern words follow similar patterns. For example, a word like Googlers can be broken down into Google as the root, indicating a person associated with an activity, hence indicating plurality. The core task here is breaking words into their basic components to understand their structure and meaning. This is what we refer to as morphological analysis. These concepts may seem basic, as many of them are introduced in high school language arts courses, in decent Florida high schools, I should say, but they are essential for understanding the range of syntactic tasks we study in natural language processing. Part of speech tagging is a very important task. While parts of speech are a basic concept in language, the goal here is to automatically annotate words or sentences with the grammatical roles they serve, such as nouns, verbs, or adjectives. This information is critical for many downstream tasks, including syntactic parsing and word sense disambiguation. We will revisit these applications later in the course. So, to summarize, syntactic tasks focus on understanding the structure of language. They aim to model how words are organized and related to one another based on grammatical rules. The next category of tasks is semantics, which focuses on understanding meaning. Semantic tasks aim to capture the meaning of words, sentences, and even entire passages of text beyond surface-level structure. While syntactic structure can often be handled using explicit rules, meaning is much harder to encode directly correctly and requires deeper interpretation. One important semantic task is named entity recognition, where the goal is to identify proper nouns such as people, places, and organizations in text. Another key task is word sense disambiguation. Here, the objective is to determine which meaning of a word is intended based on context. For example, the word bank could refer to a financial institution, the side of a river, or something else entirely. Many words, such as bank, pitch, or color, have multiple meanings, and identifying the correct one requires semantic understanding. Summarization is another semantic task. The goal is to generate a concise version of a longer text while preserving its core meaning. Sentiment analysis is also a semantic task. In this case, we aim to detect the emotions or opinions expressed in a piece of text, such as whether it is positive or negative, supportive or hostile. Applications of semantic tasks include chatbots, search engines, recommendation systems, and social media monitoring. We can illustrate this with word sense disambiguation. Words in natural language are often broad in meaning and can have multiple interpretations depending on context. For example, consider the sentences: Ellen has a strong interest in computational linguistics, and Ellen pays a large amount of interest on her credit card. In both cases, the word interest appears, but it carries very different meanings. In the first sentence, interest refers to curiosity or engagement with a topic. In the second sentence, interest refers to a financial charge added to the principal of a loan. Identifying which meaning is intended based on context is precisely the goal of word sense disambiguation. For many tasks, such as question answering and machine translation, this kind of understanding is essential. You need to be able to disambiguate words among their possible meanings in order to perform these tasks correctly. That covers semantics. Pragmatic tasks go a step further. They focus on understanding context, intent, and implied meaning in language. Pragmatics deals with how language is interpreted in real situations, taking into account factors such as tone, context, and what is left unsaid. Historically, this has been one of the most challenging areas in NLP because language can be sarcastic, ironic, or intentionally indirect. Examples of pragmatic tasks include coreference resolution, where the goal is to link pronouns or references back to the entities they refer to. For instance, in a sentence like John went to the store and he bought milk, we need to know that he refers to John. If multiple entities appear in a sentence, resolving these references becomes more complex, especially when plural references such as they are involved. Dialogue management is another pragmatic task. Here, the system must track conversational context across multiple turns to maintain coherent interactions. Speech act recognition, which identifies the purpose of an utterance, such as whether it is a question, a request, or a command, also falls under pragmatics. Discourse analysis examines how sentences connect to form coherent text. Applications of pragmatic tasks include virtual assistants, conversational AI systems, and customer support agents. It is important to clarify the distinction between semantics and pragmatics. Semantic tasks focus on meaning at a relatively surface level, such as identifying entities or determining sentiment. Sentiment analysis, for example, assigns an overall positive or negative label to text, often without deeply modeling intent or subtle implication. Pragmatic tasks, on the other hand, aim to infer an intent beyond explicit meaning. They require understanding broader context and real-world knowledge. Idioms and metaphors illustrate this well. A phrase like "aus the crow flies" cannot be understood literally. Its meaning depends on contextual and cultural knowledge about distance and direction. Understanding such expressions requires representations that capture more than surface-level word meaning. While these distinctions are conceptually useful, there can be overlap in practice. Some applications combine syntactic, semantic, and pragmatic components. Over the course of the semester, we will examine these tasks in detail, discuss where the boundaries lie, and explore how modern models integrate multiple levels of language understanding. One example of a pragmatic task is coreference resolution. We will have a full lecture dedicated to this topic, so there is no need to go into too much detail here, but a simple example illustrates the challenge. Consider the sentence: John put the carrot on the plate and ate it. As humans, we immediately understand that John ate the carrot, not the plate. This seems obvious because plates are not typically edible. However, from a computational perspective, this is not trivial. The most recent noun mentioned is the plate, and a naive, recency-based resolution strategy might incorrectly conclude that it refers to the plate. This highlights the difficulty of coreference resolution. The system must decide which entity a pronoun refers to, and doing so often requires real-world knowledge, not just syntactic proximity. Another example is: Bush started the war in Iraq. The president needed the consent of Congress. Here, the president refers back to Bush, specifically George W. Bush auteur. Understanding this connection requires linking entities across sentences and recognizing that both expressions refer to the same person. Some cases require even more complex reasoning. For example, today was Jack's birthday. Benny and Janet went to the store to get presents. Janet decided to get a kite. "Don't do that," said Benny. "Jack already has one. He will make you take it back." As humans, we can infer which kite is being discussed and why buying another one might be a problem. The context is clear to us, but for a computer, resolving these references and intentions is much more difficult. These examples illustrate why pragmatic understanding, especially tasks like coherence resolution, requires more than surface-level analysis. It demands contextual reasoning and real-world knowledge, which makes it one of the most challenging aspects of natural language processing. Let me finish with one final comparison: computer languages versus natural languages. Why are computer languages relatively easy, even though programming languages still involve compilers, grammars, parsing, and an entire field of study that many students find challenging? They are still far easier to handle than human languages. Programming language courses may be abstract and demanding, but computer languages are fundamentally more constrained and well-defined. This contrast helps reinforce the earlier point. Human languages are difficult to understand because of ambiguity, context, variability, and implicit meaning. Computer languages, by design, avoid these issues. That difference explains why natural language processing is such a challenging and interesting problem. Let's look at that comparison more closely. The primary difference between natural languages and computer languages is ambiguity. Computer languages are designed to be unambiguous. They are well-defined, highly structured, and deterministic. If you provide the correct structure, you get the expected output. There is no flexibility or interpretation involved. Formal programming languages are explicitly designed this way. Each construct has a clear one-to-one meaning, and programs can be described by grammars that produce a unique parse for every valid statement. There is no room for multiple interpretations. Programming languages are also designed to be efficient and predictable. They do not rely on context, intention, or implied meaning. When you write something like x equals y, the system performs exactly that operation and nothing beyond it. There is no inference, no ambiguity, and no additional meaning to resolve. Let's look at that comparison more closely. The primary difference between natural languages and computer languages is ambiguity. Computer languages are designed to be unambiguous. They are well-defined, highly structured, and deterministic. If you provide the correct structure, you get the expected output. There is no flexibility or interpretation involved. Formal programming languages are explicitly designed this way. Each construct has a clear one-to-one meaning, and programs can be described by grammars that produce a unique parse for every valid statement. There is no room for multiple interpretations. Programming languages are also designed to be efficient and predictable. They do not rely on context, intention, or implied meaning. When you write something like x equals y, the system performs exactly that operation and nothing beyond it. There is no inference, no ambiguity, and no additional meaning to resolve. In contrast, programming languages are unambiguous. They are formal languages defined precisely, where every statement has a single clear meaning. This is achieved through well-defined grammatical formalisms such as Backus Norform or BNF, which strictly dictate the syntax and structure of the language. As a result, when we write a statement like x equals x plus 1, there is exactly one interpretation. The system knows precisely what operation to perform, and there is no alternative meaning or contextual ambiguity involved. Efficiency is another key aspect of programming languages. Programming languages are designed to be efficient to parse, understand, and execute. Parsing, in this context, refers to the process of analyzing code structure to ensure that it is syntactically correct and can be executed properly. Common parsing strategies, such as left-to-right or top-down parsers, are designed to be highly efficient. This efficiency allows compilers and interpreters to quickly translate source code into another form, such as machine code or an intermediate representation, without ambiguity or excessive overhead. To summarize the contrast, the core reasons behind the difference between natural and programming languages are clear. Human languages are ambiguous by nature. Programming languages are deliberately unambiguous, and programming languages are engineered for efficiency in parsing and execution. I'll wrap up with a couple of slides to introduce what we will cover next lecture. More said we will cover next lecture. Ultimately, when you read words in context and you already know the language, you are able to interpret and assign meaning to those words. That is exactly what we want computers to approximate. This is what we mean by computer understanding of language. There are multiple ways to approach this problem. One of the earliest and most influential approaches is the statistical approach. In this approach, we study how language is actually used in real data and derive representations for words and utterances based on observed patterns. For example, we may learn that certain words are strongly associated with positive sentiment, while others are associated with negative sentiment. Words like good tend to occur in similar contexts as other words with related meanings. By capturing these usage patterns, we can model semantic similarity between words. These representations allow us to identify related expressions, replace words with semantically similar ones, and support tasks such as retrieval, interpretation, and limited paraphrasing. Historically, this line of work also drew inspiration from lexical resources, such as dictionaries or word banks. This is just the starting point. We will stop here for today, and in the next lecture, we will dive deeper into these ideas and explore more advanced representations and techniques. So early on, what we wanted to do was to create explicit meanings for words inside computers. One of the most common early solutions to this problem was something called WordNet. WordNet is essentially a structured lexical database that organizes words into sets of synonyms, known as synsets, and encodes relationship between them, such as hypernyms and related concepts. You can think of it as a large structured word network. For example, if you start with a word like good, WordNet will tell you that it can be a noun, an adjective, or something else entirely. As a noun, it might relate to concepts like goodness or benefit. As an adjective, it might mean honorable, respectable, beneficial, or similar notions. All of these meanings are connected through explicit relationship between words. Or, at first glance, this looks great. You might ask yourself, if we have WordNet, why do we need more advanced models like modern language models? The issue is that building and maintaining such resources requires a tremendous amount of human effort. Someone has to manually curate the meanings, relationships, and structures. This becomes especially challenging when you consider the sheer number of languages in the world, on the order of thousands, each with unique structures and characteristics. Another major limitation is that language is dynamic. New words and new meanings emerge constantly in everyday life. Younger generations introduce new expressions, slang, and usage patterns that are not immediately captured in static resources like dictionaries or word networks. Even within the same language, meaning can vary significantly across regions, dialects, and social contexts. There is also the issue of nuance. Words that appear as synonyms in a resource may not be interchangeable in practice. For example, proficient might be listed as a synonym of good, but the strength and implication of those words can differ depending on context. In everyday usage, people often say things like, "This is amazing," when they really just mean, "This is good," or they say good when they actually mean excellent. Context matters enormously. In some settings, good might mean outstanding. In others, it might mean mediocre or even insufficient. For example, in certain evaluation systems, a rating of good can actually be a negative outcome. So the same word can convey very different meanings depending on the situation. All of this highlights why purely symbolic, dictionary-based approaches struggle to fully capture language. Meaning is not static. It evolves with context, culture, usage, and intent. This is precisely why more flexible, data-driven representations became necessary and why we moved beyond fixed word networks toward modern language modeling approaches. Here are some other issues with WordNet. Missing new meanings is another major limitation. Words like wicked, badass, nifty, wizard, genius, ninja, or bombastic often carry meanings today that are very different from their original definitions. If you talk to a high school student, you will quickly realize that there's an entirely new, evolving layer of language being used on the street right now. There is also a varying degree of subjectivity. Word choice is personal, and different people use the same word in different ways, often without meaning exactly the same thing. This subjectivity makes it difficult to fix meanings in a rigid, predefined structure. Another issue is the amount of human labor required. Creating and maintaining these resources requires continuous human effort. Language evolves constantly, and keeping such systems up to date is labor-intensive and does not scale well. Finally, these approaches struggle to compute accurate word similarity. Even if two words are related, such as cat and dog, which are both animals, they may appear far apart in a dictionary-based structure. language. The system cannot easily infer how similar they are or how closely related they should be, beyond explicit links that someone manually encoded. These limitations collectively explain why early symbolic approaches, while valuable, were not sufficient on their own, and why more flexible, data-driven representations of language became necessary. Thank you, everyone who was with us online, and the recording will be made available as soon as possible. Thank you.